We're going to explore linear motion under constant acceleration, focusing on the Suvat equations. These equations are key tools in physics for describing how objects move when they accelerate at a steady rate. We'll break down each part step by step to understand how displacement, velocity, acceleration, and time relate to each other in straight-line motion. This will provide a solid foundation for solving a variety of problems related to motion. Let's get started.
To apply UVAT correctly, we need to make sure a few conditions are met. First, the motion should be in a straight line, meaning the object moves without changing direction. Second, the acceleration must be constant throughout the motion, so it doesn't speed up or slow down irregularly. Third, there can't be any changing forces acting on the object. The forces should be steady to keep the acceleration uniform. Finally, the time intervals we use to analyze the motion need to be uniform, so we look at consistent segments of time. Meeting these conditions helps ensure our calculations and predictions using UVAT are accurate. Let's review some key terms that will be important as we work through the equations of motion. Displacement, represented by S, is the distance moved in a specific direction and is measured in meters. Initial velocity, or U, is the speed of an object before it starts accelerating, measured in meters per second. Final velocity, V, is the speed after a certain period of acceleration, also measured in meters per second. Acceleration, denoted by A, tells us how quickly the velocity changes, measured in meters per second squared. Lastly, time, T, is the duration over which the motion occurs, measured in seconds. Keeping these definitions clear will help us apply the SUVAT formulas correctly. In this part, we focus on the idea of constant acceleration. This means that the acceleration remains steady and does not change over time. Because of this, velocity increases or decreases at a constant rate, which means it changes in a straight line when you graph it. Position, on the other hand, changes more rapidly and follows a curved path or quadratic pattern on a graph. These predictable patterns in acceleration, velocity, and position help us understand and anticipate how objects move under constant acceleration.
This equation tells us how the final velocity of an object changes over time when it's accelerating. It starts with the initial velocity and adds the increase in velocity, which is the acceleration multiplied by the time. This relationship is useful when we want to find the velocity at a certain time without worrying about the distance traveled. It's a simple, direct link between velocity and time, showing how velocity increases at a constant rate when acceleration is steady.
This equation helps us figure out how far an object moves over a certain amount of time when it's accelerating. It combines the initial velocity, the time, and the acceleration into one formula to calculate the displacement. The important thing to note here is that the displacement depends on time squared, meaning the distance doesn't increase just in a straight line, but accelerates as time goes on. We use this equation specifically when we don't know the final velocity of the object, but still need to find out how far it has traveled in a certain time period.
Now, let's look at the third SUVAT equation. This one is useful because it's written without a time term, so it's the go-to formula when you don't know the time involved in the motion. It's derived from the other equations we've discussed, combining initial velocity, acceleration, and displacement to find the final velocity squared. This equation helps fill in gaps when time isn't given, making it a valuable tool for solving motion problems efficiently.
This equation represents the fourth SUVAT formula, which calculates displacement when you know the initial velocity, final velocity, and time. It works on the principle of average velocity, meaning it takes the sum of the initial and final velocities, divides it by 2, and then multiplies by the time elapsed. This formula is only valid when acceleration remains constant throughout the motion. It's a useful way to link how far an object has traveled with the time it has been moving without needing to directly involve acceleration in the calculation. When choosing the correct equation to solve a problem, start by identifying the variables you already know. Then, determine which variable you need to find. After that, pick an equation that includes all the known variables but does not leave out the unknown one. Finally, make sure the units of measurement in your equation are consistent and work together correctly. This approach helps ensure you select the best equation for your specific problem. Let's look at how a velocity time graph works. When an object accelerates at a constant rate, the graph forms a straight line. The slope, or gradient of this line, represents the acceleration. The intersection point on the velocity axis shows the initial velocity, the speed at the start of the time considered. Additionally, the area under the graph line gives the total displacement, which is the distance moved in a specific direction. So, by analyzing these elements, we can understand how velocity changes over time and calculate both acceleration and displacement. When we look at the displacement time graph, we see a parabolic curve. The gradient of this curve at any point tells us the velocity at that moment, since the slope equals velocity. Because the curve is not a straight line but curved, this indicates that the velocity is changing over time, meaning there is acceleration. The steeper the slope at any point, the higher the velocity. So the curvature of the graph actually shows the presence of acceleration, with increasing steepness reflecting an increasing speed. Moving on, this slide outlines the key points about acceleration time graphs. It highlights that a constant acceleration is represented by a horizontal line on this graph. The important concept here is that the area under this line equals the change in velocity over that time period. This area can correspond to either positive or negative acceleration, indicating speeding up or slowing down. When the acceleration is zero, it means the velocity remains constant. So, this graph is a straightforward way to visualize how velocity changes over time when acceleration is constant. In freefall, the only force acting on an object is gravity, which causes a constant acceleration downwards at 9.81 meters per second squared. This acceleration is represented by the symbol g. When analyzing motion in freefall, you can choose either downward as the positive direction or downward as negative, depending on your preference, but consistency is key. Importantly, the equations of motion we use for other types of constant acceleration still apply here, making freefall a straightforward case to analyze with these same principles. As we focus on the IB exam, keep in mind a few important points that can help improve your answers. Always state your assumptions clearly so the examiner understands your starting point. When you work through problems, show every step, especially the substitution of values into equations. This makes your process easy to follow and earns you method marks. Make sure to include units in your final answers to demonstrate your attention to detail and accuracy. Finally, use the correct sign conventions consistently throughout your work to avoid confusion and ensure clarity. Keeping these points in mind will help you present your solutions clearly and confidently. Before we wrap up, it's important to keep in mind some common mistakes that often come up when working with these concepts. First, using the SUVAT equations when acceleration isn't constant can lead to incorrect results, so always check that assumption. Next, don't confuse velocity with speed. They're related but different, so be clear on which one you're dealing with. Sign errors can also cause problems, especially when directions matter, so pay close attention to the signs you assign. Lastly, forgetting the squared term in the equations is a frequent oversight, and it can throw off your calculations. Keeping these points in mind will help avoid common pitfalls and make your work more accurate. To wrap up, remember that the concepts we've covered apply only when acceleration is constant. There are 5 key variables, and these are all connected through 4 main equations that describe the motion. Using graphs helps to make these relationships clearer and easier to understand. One important tip is always to define your sign convention at the start, so you stay consistent and avoid confusion throughout your calculations. This summary highlights the core ideas you need to keep in mind moving forward.